Um, okay, so hello everyone. I'm Dev Mehta and I'll be taking the maps part of today's session. First of all, let me confirm if I'm audible. Am I audible to all of y'all?
Yes, Dave, you're audible.
All right, so let's get started with the session. So today we're going to cover maps. Maps are uh, so this is the content for today's session. We are going to cover maps, unordered maps, some functions of maps. So how to insert elements into the map, how to access those elements, and other functions like find, erase, and clear. So what are maps? Maps are basically an associative containers. So where you can like map some values to some keys. So if you suppose you have marks and names of students, so you want to map the marks of the student to the name of the student. So for that you can use maps, and they are so keys of a map are similar to the indices of an array, where if you access an index of an array, you get the value related to it. So if you go to a key in a map, you get the value that is mapped to it. And maps and unordered maps have one main difference. Maps store the key value pairs in increasing order of the keys. Uh, va- and keys need not be only integers. So increasing order need not be only numeric. It can be lexicographic also, which is in terms of strings. And the last point, maps are implemented by using red-black binary trees. And this is actually not very important from the perspective of competitive programming. It is an advanced data structure. You can just know this as supplementary information. So what are unordered maps? So as I mentioned earlier, unordered maps are maps where there is no certain order, no increasing or decreasing order of the keys. And there is a difference in implementation also. Maps are implemented using red-black binary trees, while unordered maps are implemented using hash tables. Now, hash tables are also not very necessary to know, but I've attached a Geeks for Geeks link in case any of you want to find out what maps are for. And unordered maps are beneficial because the time complexity of finding or accessing an element in an unordered map is less than the time complexity to find or access an element in a map. So when a map, if you want to find a key or a value, it takes log n time, whereas in an unordered map, it takes only O of one time. So depending on the time constraints of the question, you can decide whether to use unordered maps or maps. But there is a certain disadvantage with unordered maps. You cannot use all the data types with unordered maps. So like you cannot use say in a map you can use another map as a key in it, but for unordered maps you cannot use another map as a key value in it. So this is the basic declaration for unordered maps. You put unordered map, then data type 1, data type 2, and the map name. Now coming back to maps, because maps is the main focus of this session. So how to declare a map? We put map, then data type of the key, data type of the value, and the map name. So data types can be of any type: char, int, boolean, string. So here there's an example where we map an integer which is marks to the name or the ID of a student. And as I mentioned earlier, maps store the keys in increasing order. But what if you want it in decreasing order? Then you can use this while declaring your map. Then it will store the key value pairs in decreasing order of the keys. So I'll just quickly go and declare a map. So here I'll go. You can declare anything for the key and the value, but here I'll do a string in combination. Let's call it M. So yeah, that's basically just a map that I've declared. Now let's learn how to insert elements in this map. So we can either directly put the map name and use the square brackets to define a key, and then we can assign a value to it. So I'll just go there and do that once. So M is our map name. A key is of string type. So the first one in the map declaration is the key, and the second is the value data type. So our key is of string data type. So we put it in double inverted commas, and let's just say my name. Let's call this marks, and marks of Dave. So I mean, I'll give myself good marks only. So let's say 96, and let's define it for my good friend Aditya. Let's say 90. So this is how you assign values to the keys in the map. There are also other ways where you can use the insert function, where you insert the entire key value pair. So map name dot insert key comma value. So this entire pair gets inserted into the map. And note, you cannot use this to change the value assigned to a key. So if you declare it like this map name square brackets key, then you can change the value that is assigned to this key by using this format. But here, if the key already exists, then this will not work. And you can also use the emplace function. Uh, there's a typo here. It's supposed to be emplace, not empace, which is similar to the insert function itself. So yeah, that's how you insert elements. Now, this is how you access elements in a map. So maps are pretty simple data structure. So there's just some complexities with accessing them where you need iterators. And as you have seen in the last session, you can use auto iterator to iterate through the entire map. So this is one of the ways you can access the entire map. And this is the second way. Both of them are the same, but auto simplifies things a little when you're using it in your program. So I'll just go back and write a simple function to print the values that are inside our map. So map, if you want to use string int, we keep that the same. And let's just use auto because it's simpler. And here we need to put an and because the value that we are passing is a reference to the map. We need to use this ampersand and cout. So here I've shown you how to access the elements of the map. So when you want to access the key, you do star iterator dot first. So when you use a map, it stores the values in pairs. So when you do star iterator, it gives you the pair. And when you do dot first, it gives you the first element of the pair. And when you do dot second, it gives you the second element of the pair. So the first is the key and the second is the value. So make sure that you remember that this is not contiguous. So maps aren't storing values like arrays, which are contiguous. Maps are storing pairs in different places in the memory and have linked each other. So we use iterators. And when we do star IT, when we access that iterator, we get the pair. And from that pair, we can have the key or the value depending on what we put, dot first or dot second. So cout, let's do star IT dot first. This is the key. And there's also one more way we can do. Instead of star IT dot first, we can do IT and point to the first. So IT and a arrow symbol towards the first one. So this is value. I'll show you what I mean. This is the same as what we have written here. This thing and this thing mean the same. So, and then so just go ahead and print So I've run into a problem here. Just a minute. Okay, so the issue here is, since I've already used this as an address, so we don't need to use the star IT. We can just do it.first because it is already pointing to the pairs inside the app. How it should work. Okay, there we have it. So key is Aditya and value is 90, and key is Dev and value is 96. So as you can see, the keys are arranged in increasing order. And this is lexicographic. So Aditya comes before Dev in the dictionary, right? So lexicographic order is basically the dictionary order of the strings. So yeah, that's how you print and access the elements in a map. Do you guys have any doubts till now? Like y'all can mention it on the Slido or in the Teams itself. Yeah, so as Aditya mentioned, we can remove the and in the for loop and use star IT, or we can use the and then directly use IT. Because does anyone have any doubts? I know the syntax is a bit complicated for maps, but once you start using it, you'll get used to the syntax and you don't need to go much into detail. So there's always a CPP reference, which is a very good site where you can find out all the functions related to a map and the syntax of the map. I'm hearing someone requested to see the code. So here's the code. We're going to add to it. So yeah, there's the code. Now let's get back to the presentation. And so these are some other functions related to maps. So as I mentioned, CPP reference, it's a great site where you can find all the functions related to map, their syntax. And if you, by most of the functions, by seeing the name of the function, you'll understand what it does. But in case you don't, you can search that up on Google and find out how to implement it or how to use it, apply it. So I'll show you the functions here, how to use them in your program. So there's erase, find, size, and clear. So let's just use size first. So pretty simple. If I have m, I'll do cout m dot size and end l. This will give you the size of the map, which is the number of pairs in the map currently. So here, this 2 here, that is the size of the map. Now, I'll just add a few more values so that we have something to erase later. Otherwise, we won't have anything. Let's put Ved. Ved is the opposite of Dev, so we'll give marks also opposite of Dev. And let's put Ramesh, I guess. And let's say 2. Who cares? I'm just trying to make the output a bit more better to look at. So now if I print the marks, you will see the size has changed to 5. And this is yet in lexicographic order. A comes before D and similarly this follows. These are the marks, which are the values, and these are the keys. Now, if I want to erase something, I can simply do, before I print, I'll do marks dot erase. I put the key here. So let's say I want to erase Mahesh's marks. So once I do that, yep, here I go. So Mahesh is not anymore in the marks list. And okay, so let's just comment that out for now. Let's use find. So I've used erase, I've used size. Now we'll use find. So find returns the iterator to the pair which is having the specified key. And if there is no such element, then it returns the map name.end, which is a point, which is the iterator, which is after the last pair of the map. So if you do map name.end and access it, you won't get anything because that is one after the last pair. So yep, let's do find. So we can make it complicated and do map string int uh, iterator it, then it equals to marks dot find and whatever value or key that we want. But rather than that, it's better to just do auto it equal to marks dot find, and I'll find way in here and see out marks it. Uh, sorry, see out it dot first and it dot second, and then I'll comment the print out for now because we want to print only the value corresponding to weight. Just a minute, I think I commented out something important. Okay, here we need to do star it dot first since I have not put the ampersand before. I made this mistake earlier also, I shouldn't have done it again, but yeah, so we need to put star it here since we've not put the ampersand earlier. If I had put this ampersand earlier, then I could directly do it. Yep, so this has given us the marks that Ved has received. Ved, that's 69 marks. And similarly, you can do Mahesh also. But there's one issue. If I put in a name that's not in this list, so if I put in, say, if I put in ABC, then it won't, it will give us an out of segmentation fault because there is no one called ABC in this map that we have. So instead of this, we can put an if statement. So if it is equal to marks dot end, because our iterator, when we do find key, the key value when we put the find function returns the iterator to the pair if it is there, and if it is not there, it returns the iterator to the end. So if it returns the iterator to the end, we say none because there's no one called ABC in our function. Else we print the name of the person that we want. So see, none, because ABC is not in the list. Anything we put here which is not in the list, it will return none, because our find function is returning the end iterator to the end when there is no element detected. And if we put weight here again, we should get weight 69. Yep. All right. So that's how find works. Comment this out. And here we have, let's do print marks again. There's another function called clear. What it does, it clears all the pairs in the map. So it's very simple, marks dot clear. If you run it now, you'll have no elements in the map. So the size is 0, the size that we outputted here, and it prints nothing because there's nothing in the map to print. So that's about it for maps and what all functions are there in maps. And next we'll go to an application. So this is a very simple question that we can solve using maps, and think about how you would solve it without using maps. It would be very complicated uh, because you have to print unique strings in lexicographic order with their frequency. So this, if we had to do with integers, it would be easy because we could use an array and we can use the index of the array and map it to the value in the array and do plus plus for the index. But when you do it for strings, it becomes very complicated. But since we have maps, we can do it in simple, in a very simple way. So I'll give you all a bit of time to think about this. Let's say 2 minutes, and then I'll show you all the code for it. And I'll also explain you all some complexities that we face with maps. So I'll give you all 2 minutes up till 5:30 to try the question on your own. And until then, if you all have any doubts, you all can ask in the chat on Slido, or you all can unmute and ask. So yeah, here's the question. All right, did you all try it? So yeah, it's almost 5:30 now. I think there's enough time. The question was pretty simple. So I hope everyone's at least tried it once, or at least thought about how you would use maps here. So yeah, this is it. This is all that you need to do when you're using maps. On the other hand, if you were not using maps, then you would be in a big mess. So since we need to take string input, we have to take n unique strings, and we have to print the unique ones. The strings need not be unique, note. So first we'll take n as an input, run a loop for n, 0 to n, to take the n strings. And we take input of the n strings here, cn, yes. Yep, sorry, I got disconnected for 1 minute. So yeah, you take the string input here, CNS, and then you do map of S plus plus. So I'll show you when you add an element here. So if I put marks of say ABC. If I just initialize this and I don't assign any value to it, so it will automatically be given a value 0. So I cleared this. Let's comment out the clear function. ABC has the value 0 automatically. So that's how maps work here. If you initialize something but don't assign a value to it, it gets initialized to 0. So here when we do MS, when we make MS here, our map is named M and the string is S, it's automatically initialized to 0 for the key S. And every time we find that S, we do plus plus. So first time it's 1, then it's 2. If we find the string again, then it's 3. So that's basically the same thing as you do for when there are integers and you need to find how many frequency of integers. And then this is just the print function, which is pretty standard. We've used it here also. So now let's give it an input. Let's say I'm going to give it 10 values. A, B, C, D, E, F, H, I, J, A, B, C, A, B, C, D, E, F. How many is that? 1, 2, 3, 1, 2, 3. That's 6. A, B, C, D, E, F, H, I, J. That's 9. And let's give D, E, F again. That's 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2. That's 10. So I hit enter. And this is our output. ABC 4 times, DEF 4 times, and HIJ 2 times. So we have our strings, unique strings, and the frequency of each of the strings. So here if we check ABC appears 4 times, ABC appears 4 times, DEF appears 4 times, and HIJ appears twice. So that's correct. And it was a pretty simple function, not very complicated. Do you all have any doubts in this? Okay, so Amandeep is saying, why haven't we used asterisks here? So we are not using iterators here, right? We are assigning, when we do auto IT, this is the iterator. Like for assigning the values and increasing it, we can just do ms plus plus 0. It will give the values 1, 2, whatever is the frequency. And here, when we are doing, we are not passing m as a reference. Over here, we are passing m as a reference. So that's why we need to use either and ampersand here or use asterisk here. But since in the given question, we have m in the same function, here the map we are referencing in the print function, but it is declared in the main function. We are passing marks here in the print function. We are passing marks in the print function, and or I'll just remove the print function. It will be simpler for you. Now you don't need to use the star because we are not passing it anywhere. It's in the same function, the declaration and the map. So here we'll put marks instead of m because there's nothing called m anymore. So I think you can now understand why we don't need to use any asterisk or ampersand here, because m has been defined here. We are accessing it over here. Auto iterator is basically, it will go through all the pairs in the map. It would be covered in the last session, I believe. All right, understood. That's great. So yeah, that's about it for maps. Now, these are two of the problems. So this PDF will be shared with you after the session. You can go and practice these two problems. They're very basic problems using maps, whatever you've used in this function. So the only thing about maps, this is the attendance QR. So just scan the QR and give your attendance for today's session. By that time, I'll just tell you all a bit about maps. So the syntax is a bit complicated. You initially you might think it's difficult to use, or why is there so many different functions, or where do we put ampersand, where do we put the asterisk. But once you start using it, it's not that complicated. And anytime you have any difficulty, you can look it up, go to CPP reference. You have all the resources available. You can come back to these slides and check out where you need to use the asterisk or where you don't need to use it. So I believe that's about it for maps. Give your attendance, and then Aarav, my colleague, will take over this session. I'll give you all 1 minute, 2 minutes to, give attendance, go to the form. I think somebody asked what's auto. So I'll just quickly, it should have been covered in the last session, but I'll quickly go and tell you all what auto does. So I wrote it earlier, but I'll just write it once again. So there's two ways we can start iterators. So we can do map. This is the kind of map we are using. Then we use scope resolution, iterator, IT, define this iterator. Then we can run a for loop where we do IT equal to marks dot begin. So what this begin does is it gives you the first pair in the map. And when IT is not equal to marks dot end. So you can see what I'm doing here, right? I'm going through the entire map and IT plus plus. The one thing to notice in maps, you can't do IT plus something else. You need to do IT plus plus or IT minus minus because that's how STL and maps is defined. And here you can, do C out IT first and then IT second, and then this thing is the same as this thing. Auto is just saving us the time of writing all of this. We don't need to write all of this if we are using auto IT. So that's about what auto is. Auto just simplifies things and compresses them, saves us time. And that's why it's better to use auto. I have shown this in the slides also, so you can see. This is how you do it with auto, iterate through the elements, and this is how you do it without auto. This is definitely a bit more complicated and a bit more lengthy than what auto helps us to do. All right. So back to the attendance slide. Aarav, you may take over whenever you want to.
All right, guys. Am I audible? Can someone please confirm I'm
Yes,
audible?
yes, Aarav, you are audible.
Oh, okay. Okay. All right, guys. Hello, everyone. I'm Aarav Giri, and today we'll be doing modular arithmetic. All right. Let me just share my screen. I think the screen should be visible now.
Your
Is the
screen
screen
is
not
not yet
visible?
visible.
Okay, let me try again. Is it still not there yet?
Now it is.
Is there? Just a minute. Is it still not visible?
No, Aarav.
It's okay. We have little time. I will try to resolve it. A new source. Is it still not visible?
The screen is visible now.
Yeah, finally. I think the best solution to all of this is refresh. All right, let's waste no further time. Let's get right into it. I think my audio is also clear.
Yep, everything's perfect. Continue.
Okay, let's go. Modular arithmetic. Just a minute. So what is modular arithmetic all about? You know that a number can be written in terms of another number in the following way. If we have a number n and I divide it by a number d, you get a quotient q and a remainder r. And this, as you recall, is basically Euclid's division lemma. So now you know that there is something called a remainder. All right. So modulo arithmetic is basically relating two numbers along with its remainder. All right. Let's go. So this modulo operator is basically going to give you the remainder. All right. You might have, I guess, already used this, but here, let's see it one more time. A% B is basically the remainder when A is divided by B. All right. And it is very easy to see through these examples. What is 10% 3? It is 1. 15% 5? It is 0. 0% any number is 0. And remember one thing. The second number can never be 0. Because why? Not a single number is divisible by 0. All right? Fine. So now, these are some of the common properties. Okay. Let us see them one by one. First of all, A plus B percent M. What does it say? I add two numbers and calculate its remainder. All right. Now you might want to say directly that, okay, I will just divide A by M. I'll divide B by M and then take the whole and take its remainder with M. So I can't see, but let me give you a reason why. It is possible that the sum of the remainders will exceed M, will be greater than equals M. And you know one thing about remainder, all right? Remainder of a number, of a division operation will lie from 0 to 1 less than the divisor, in this case M. So it will be 0 to M minus 1. So if this sum becomes M, suppose I'll take 1 plus 2 modulo 3. 1 plus 2 modulo 3. So you know what is 1 modulo 3? Answer is 1. And what is 2 modulo 3? Answer is 2. 1 plus 2 is 3. Okay. Now if you just leave the answer like that, I will hide this. Okay, I'll hide this. So if I just report the answer as 3, it is wrong because left hand side has a remainder operation. When you're dividing something by 3, there should be either 0 or 1 or 2. It cannot be 3, which is why we put this additional modulo operation. All right, I hope this is clear. Similarly, in division, we are going to do this. A minus B modulo M is A modulo M minus B modulo M plus M modulo M. Now, again, why is this plus M there? Remember, whatever operating here to prove all these identities involve to a correct form. Your remainder should lie from 0 to M minus 1. Now, A% M and B% M, when you take the difference, yeah, it will not exceed M, but it can get. All right. So to avoid that, M over there. Suppose I'm this difference, A% M minus B% M. If I'm getting the difference as minus 1, I cannot simply do -1% m. To take care of that, I'm just adding m. Suppose 3. Then it'll be 2 modulo 3. And 2 modulo 3 is 2, which is fine. All right. That's the rationale behind adding m over here. Now, what is a into b modulo m? It is a modulo m into b modulo m whole modulo m. All right. I think I had just written the proof of that. Let me just show it once. So see here carefully. This is in general. I can write a number as q into d, quotient into divisor plus remainder. Formula. Now, in modular arithmetic, we write it in this manner. N equals R modulo D. Alright. So now, what was it over here? It was A into B modulo M. So now A into B equals this much. I mean, A into B equals this much. Okay. This basically P times B plus some remainder R1. And similarly, I wrote something like this Q into D plus some remainder R2. Then what happens is some multiple of D plus R1 into R2. Now, when I write it in this manner, okay, when I write it this manner, I will say A into B equals R1 into R2. And similarly, R2 will be given by B modulo D. This is all with respect to D. But note that the product, like here I had spoken about sum and differences being out of range, you can say. Similarly, over here, to ensure it is in that 0 to D minus 1 range, I'm going to take the whole modulo with D. Okay. This mod is basically percent. Just don't be confused with this. Okay. Let me just clear it up. So they should explain why I'm taking again whole modulo M. Now, the interesting part. What about division? This is very intuitive, right? A by B modulo M equals A modulo M by B modulo M whole modulo M, right? I think it's a very pleasing formula. Unfortunately, it is a wrong formula. Let us directly see what is this. Suppose I take that example. You can see that A modulo M can be less than B modulo M. Alright. If A is greater than B. So if that become a fraction and we are finding integers. All right, keep in mind it's for integers. So this is a very wrong concept. So what is something called modular inverse, which we will get to in a little while. Just a moment. All right. I hope I'm audible here. All right. Okay. Let's go with this example. To highlight an important point. Free hats. Being an IRF 1 for 8 consecutive years, the director decided to give out free hats to all the students present in the campus. Everyone in IIT Madras loves free hats. So all of them went to collect hats, and equal number of hats as well as students were present. Seeing everyone in a queue, the director wondered, in how many ways could the hats be distributed? Since he is busy, he wants you to calculate the number of ways hats can be distributed when n number of students are there in the campus. All right. And here are some values for n. What does the question say? The question basically says you have n hats. You have to distribute all of them to n students, so that each student gets one hat. I'll just give you a few seconds. All right. And one thing I want to highlight here is that assume you have to code this out. Okay. Into a C++ program. In fact, I will do it in a while. First of all, I want all of you to come up with the answer in a split second. All right. Let us just code this out once. I'll just show. Hopefully, all of you came up with the correct answer. Okay. It is supposed to be, just a minute. The answer is supposed to be n factorial. All right. Cool. Now let me just code this out here. All right. What's given? An integer n. Let me take it as a very big integer. This is, by the way, long. All right. Because you can make out that given the sizes. All right. Let me just show this. Yeah. Suppose you're calculating the factorial of 24. It's going to be a huge value. So that's why I want the largest, what do you say? Variable with largest memory that I can store. That is long int. Okay, I've done C in n. Now, I have to report the answer as n factorial. So now, let me just run a simple for loop. Okay, going from 1 to n. And then whenever at every iteration, I have to multiply answer with this I. All right. Okay. So let us see this. The first case was n equals 5. Answer is 120. All good. What is the second case? It was 16. Okay, let's try 16. Can you see this value? Pretty large value, right? No worries. It's still showing very good results. Only thing is, now it will get interesting. 21. Oh, it became negative. And as you can see, now if I try for values greater than 21, say 24, it has completely exceeded. So in theory, you can calculate the factorial and report the answer as the factorial. But the only thing is, you cannot store it anywhere. It's a very large value. I hope you're getting my point. It's a very large value. In fact, I think somewhere between, I think around 19 or 20, I'm not sure. That's the largest factorial you can compute and store it. For larger values, you cannot do that. Okay, let's get back. I just showed you how you get all these answers. So storing these values was basically the main issue over here. So first of all, as I said, long int has some, it is the maximum, it has the maximum size. Is the integer data type which has the maximum size with which you can store even the largest integers. But there is a limit to that, as we have seen. So what happens is something called an integer overflow. So it is for this reason why many times in questions they say report the answer modulo 10 power 9 plus 7. All right. We have to report the answer modulo this large value. All right. I'll come to this value in just a moment. So now you may even ask the question, how will we calculate the correct modulus if we can't store the real answer? And that's where the properties that I just came across a few slides ago will come into hand. It'll be very handy. All right. So what I will do is I have to basically use the multiplication property. So let me just show it in this example. All right. You can see here, this is where the overflow is happening. This is where it's becoming negative. All right. If you want, I will show you for n equals 21. Yeah. Till 20 factorial, it is showing pretty good results. And after that, once you multiply with 21, everything's gone. All right. So now what I will do is I will do answer equals answer times I modulo this large number capital M. All right. If I am asked to report it modulo this number, then let me see if some integer overflow happens. All right. Yeah. See, and I hopefully you can see this value. If not, I'll just let you know that for 21, instead of a negative value, we are getting a positive value. Okay. Basically, we didn't get any integer overflow. So this was the main rationale behind using this modulo operator. You're reporting the answer modulo 10 power 9 plus 7. All right. So as I said, you can compute the answers, but you cannot store it. So what do? We always use modulo some big number. Yeah, and it, as I have shown you, it can be stored till 20 factorial. And at every step, we have to include that modulo. All right. Don't do that at the end of your answer, you're doing modulo and then say, Aarav, it is not working. No, you have to do it at every step. Only then it will work properly. Okay. And why 10 power 9 plus 7? First of all, if you have seen questions, they many times they'll give you the range till 2 into 10 power 9. All right. So we needed a prime value. See, this is also a prime value. So we needed a large prime value. It consists of 10 digits. So it is good for our purposes. So since it's also the first 10-digit prime number. All right. And it's falling in the integer range. That's the main point here. Since it's falling in the integer range and it's pretty good enough to, report the remainders. And we know one thing, that the remainders will not exceed too much also. So that's why we use this value. All right. So later on, when you see problems, you need not break your head. Why have they given this? You just need to know that it's a very large value. It's a prime number. My job is to calculate everything modulo this number. That's it. Who knows? They can give 29 some other day. They can give 61. But this should be sufficient for now. All right. Now, a very important topic. So far, what we discussed was pretty easy things. Now, this is something that is a bit important that needs little attention. Modular inverse. Okay. And here by modular inverse, I mean multiplicative modular inverse. All right. Keep that in mind. So, the modular inverse of A mod M is defined in this manner. If I is the inverse, when you do A into I, this multiplication, right? That's why it's called multiplicative modular inverse. So A into I modulo M equals 1. If this is the case, then I is the modular inverse of A modulo M. All right. And remember, this modular inverse only exists if A and M are co-prime. And what is co-prime? GCD of A and M is 1. So then if M is a prime number, then there always exists a modular inverse. All right. Now, a mathematical thing. Let us come to Fermat's little theorem. It states that in A mod M, as long as M is a prime, A power M mod M equals A mod M. All right. So I can also write this as A power M minus 1 modulo M equals 1 modulo M. Pretty trivial result. All right, pretty trivial simplification, I must say. Now, observe that A power M minus 1 can be written as A into A power M minus 2. So what did we get? What did we get? A into some value, whole modulo M equals 1. Okay, 1 modulo M. This means that by the definition of inverse, A power M minus 2 is the modular inverse of A mod M. All right. And you can see this question below here. Pretty interesting question. Because your M is itself so large. Your M is 10 power 9 plus 7. And you're saying A power that much. So how will we calculate the inverse? All right. Now I can tell you one way. You run a for loop. How many times? M minus 2 times. And then at every step, just like we did for factorial, here we have to multiply A. And then you take whole modulo M repeatedly. The only thing is you notice that M is also very large. If you try to do 10 power 9 plus 7, roughly 10 power 9 iterations, you will just exceed the time limit. Okay. So that is obviously not desired. Thing is, yes, since we need the modulus with M, we will use a new method. What is it called? Binary exponential. Binary exponentiation. All right. Basically, suppose we have some power. Okay, we have something raised to a power n, x power n. We are going to split it into two halves and then return its value. All right. So suppose n is 0. Just listen carefully. This is the general algorithm. We will then code it out. If you have x power n, at n equals 0, we have to return 1. If n is an even number, that means n can be divided into two equal halves. X power n by 2 into x power n by 2. We can write it in that fashion. Suppose 2 power 16, I can write it as 2 power 8 into 2 power 8. However, if n is odd, suppose 2 power 17, I cannot write it as 2 power 8.5 into 2 power 8.5. It is pretty pointless. So I will take out one 2 from it. So in this case, I'll take out one x, then n minus 1 is even. Then we are going to recursively do this thing. All right. So suppose we have 2 power 17. I separated one 2, then I have 2 power 16. Then I will split 2 power 16 into 2 power 8 into 2 power 8. All right. Then this 2 power 8 can be written as 2 power 4 into 2 power 4. And you can see n is reducing by 2 every time. And finally, you will reach a point when n will become 0, 2 power 0. That is when you have 2, it will become 2 power 0. After that, 2 power 1 will become 2 power 0. Then we return 1. All right. Okay. So I guess you have got the basic idea that it will be a recursive thing. All right. It will be a recursive thing. Just a minute. Yeah. Now let us code it out. First of all, I will just show you something. Suppose I'll first show you, then I'll just show you binary exponentiation, and then I will show you how you will slightly modify it to calculate modular inverse. It'll be obvious by then. All right. All right. I took two numbers. Then finally, what I want to do, I will make a function called bin x, basically binary exponentiation. All right. And this should return, this should take two values, two long int values. Just a minute, my bad. Yeah. It should take two long int values. Okay. Or if you wanted to, yeah, I'll change it to x and n because then it will make more sense with what I just displayed on screen. All right. So it is saying that x power n I'm sending. Okay. I've just sent the base and the exponent over here. First of all, this is the base case of our recursion. If n equals 0, what we should do? We should return 1. No questions over there. Now I will store. Notice that irrespective of n is odd or even, I have to split it into two halves. All right. And suppose it is 2, listen carefully. If it is 2 power 17, then I'm splitting it as 2 multiplied by 2 power 8 into 2 power 8. All right. So I can actually, what I can do is, I can directly write 17 by 2. If you do integer division, it is going to give you 8 only. All right. Which is the same thing as subtracting 1 from 17, and it'll give you 16, and then you divide by 2 and then you get 8. So I will just, calculate this value. I'll tell you why am I calculating this value right now. All right. Binary exponentiation of x power n by 2, as I have done here. X power n by 2 into x power n by 2. All right. And if you notice one thing, X power n by 2 into x power n by 2. What is it? I'm multiplying it twice. The thing is, I don't want to multiply it twice. If I don't want to call the same function twice. Like what I'm saying is that if n is divisible by 2, what is written over here is I should return this value. Okay. Now observe that already when I have called this function, already when I have called this, why should I again call the same function? For very large values, it will consume a lot of time and is unnecessary. It is for this reason I'm storing it in this value. All right. Res basically result. So let me replace this by res result. Okay. If it equals this, return result into result. Else, what do you have to do first of all? If it is 2 power 17, I'll take out a factor. I'll take out x from it. Else, return x into result. There you go. Okay. First of all, this is the general code of binary exponentiation. All right. This is the general code. Let me just show you for an exam as an example, so that it's clear that the code is working. Suppose I'll calculate 2 power 13. It is 8192. All right. We got that in an instant. 8192. And suppose you had 2 power 12. Just a minute. 2 power 12. Yeah, 4096. You can see that it's clearly working. All right. Now the question arises, how will I use this method? How will I use this method to find out the modular inverse? All right. First of all, this division thing. All right. For division, I have to do I have to say a by b modulo m equals a modulo m into b modulo m. Okay. Whole modulo m, where it is an inverse. All right. It should actually be over there b inverse modulo m. Okay, that has to be corrected, but you have to get that. It is b inverse modulo m. That b is the inverse of this denominator thing. All right. It's basically saying a by b is ab inverse. All right. This much should be clear. Okay. So what's the inverse? We just found out over here. The inverse is a power m minus 2. So over there, when we are calculating inverse of b, it will be b power m minus 2. All right. It'll be b power m minus 2. Okay. So my objective, now let me just show you this. Just a minute. I'll just modify the variables. All right. All right. Let me just explain what's going on. Now, the question will be, it's there in a problem set as well. The question will be calculate the modular inverse of a given number. This given number is B. Okay. So if this given number is B, what am I supposed to do? I'm supposed to calculate B power m minus 2. It is modulo capital M, by the way. All right, it's modulo capital M. And we just did that modular inverse, multiplicative modular inverse of A modulo M is A power M minus 2 modulo M. So if it is B, it will be B power M minus 2. All right. So now what this is doing is that it's transferring this value. This is the initial value, B and M minus 2. All right. Now what we need to do, as we did in that factorial example, we have to put modulo M everywhere here. All right. So now we have to carefully do it. Now see, if n equals 0, we return 1. Now this LL result is binary exponentiation of x and n by 2. I'm splitting it by 2. All right. Now the first thing I want to, when I'm returning result into result, I want to actually return its modulo. All right. I want to return it as modulo capital M. I'm doing that at every step, as I said. So what is the formula of A into B modulo M? It is A modulo M into B modulo M whole modulo M. All right. So let me just show this. And don't worry, after this, we'll take up doubts also. All right. Just be a bit patient. All right. I just apply the multiplicative property here. I hope this is clear. Okay. Now, similarly over here. Over here, I will again modify this. And I have to actually, whenever I'm multiplying any two numbers, I have to take its modulo. All right. I have to take modulo M. All right. I'll show you. I think I'll show you something where it will fail if you don't take care of this point. So what I said, res into res, whole modulo M I want to do. I'll treat this as one separate entity. So it will be x modulo M. All right. And this res into res, I'm treating this as one another number. This whole modulo M. All right. All right. Similarly, now you take up this inner thing. This inner thing is result into result. And just like we did over here, I'm going to modify this thing. All right. It may look very heavy, but you can observe that we are being consistent with the properties of modulus. And this is important because the whole point of reporting an answer modulo something is to prevent overflows. Nothing much. All right. Just a minute. I think we are in a position to test this out. All right. Let me test this out for 2 modulo 5. Inverse of 2 modulo 5 is what? If you observe, 2 into 3 equals 6. And 6 on division by 5 gives you a remainder 1. So we say the multiplicative modular inverse of 2 is 3. And we want the small, and observe that maybe it's possible with bigger values also you get modulo as 1. All right. But I want the first such instance. So I will take 3 as my answer. All right. And you can see there is a mistake over here. So let me just correct that. The answer should be 3. Just a minute. Oh, never mind. I've specified capital M over here. All right. Let me change this. Yeah. So this will report everything modulo 5. Now I'll put 2 as the value. I'm getting the answer 3. Okay. Now if I had put 10 power 9 plus 7, 1, 2, 3. Yeah. This is 10 power 9 plus 7. Let me run this. All right. Just a minute. Yeah. Yeah. So the answer is this much. If you multiply 2 with this number, you will get 1 with then 7 zeros followed by another number 8. All right. And that will give you a modulo of 1. All right. So this our code is correct only. I just put a few parentheses so that we are not, what do you say? We are putting parentheses so that we are preserving the order. All right. We're preserving that this modulo is not getting multiplied by something. And now this thing is very crucial. Why we did this? We took a modulo here, and then we even took this, and then we took a whole modulo. Remember that if we have product of 3 numbers, all right, let me just write that down. If we have A into B into C, A into B into C, modulo M, then it is not, wait, then it doesn't equal A, it doesn't equal this value. All right. It is wrong. So what you are supposed to do? You're supposed to do this thing. All right. You're supposed to group them into twos and then do whole modulo M. Now this is the correct answer. All right. And here what did I do? I did x modulo M. I took out an x and inside I had to do result. All right. It was basically x into result into result. So I did x modulo M into res modulo M into result modulo M whole modulo M. All right. And this will give you the correct answer. All right. I hope this clears up this much. The product of 3 things. And as far as it's concerned, this should give you the correct modulo inverse. All right. And Just a minute. So that's how you calculate the modular inverse. In that code, you can replace capital M with anything you like, or you can make it user defined. Generally, what we do is we take it with respect to 10 power 9 plus 7, which is why I have done a hash define. All right. So in essence, I have covered whatever I wanted to teach. We discussed about modulo operator, the properties related to it. Then for division, we noted that we cannot just do A by B mod M as A mod M divided by B mod M. In that case, I had to do A mod M into B inverse mod M. All right, into B inverse mod M. And then came modular inverse. How are we supposed to do? How are we supposed to find out modular inverse of a number? In that case, we used Fermat's Little theorem and said that if M is prime, and for all our practical purposes, at this stage, we'll be given M as prime only. So then we need to do B power M minus 2 modulo M. Then we saw that M can be very large. So if M is very large, so then we came up with a good way, all right, of repeatedly dividing it into 2. And you know that dividing by 2 takes logarithmic complexity. I had even explained that in my binary search class. So that's why binary exponentiation is a good way of saving time and calculating such large values quickly. And then to report modulo M, we just replace everything with everything modulo M. All right. And we carefully wrote that out. And if you see power function, now the thing about power function is that it uses double and double loses precision. That's why I'm talking about binary exponentiation here and not modular inverse. So actually the thing is, you can even write your own power function using binary exponentiation. A power B, you can write it in a similar way. If you put that in the power function, then for large values, you will lose precision. It drops massively after some 15 or 18 digits. All right, because it's double. Double can store very heavy data types. You can store numbers greater than that 20 factorial I said, right? After that 21 factorial onwards, you get negative values. You can try storing it, but digits are not accurate. That's why we avoid doing that. I hope this is clear. All right. So, so I'll be displaying this attendance QR right now. If anyone has doubts, I'm sure at least one doubt I will find. I will be checking the chat as well as you could share it off in Slido also. All right. First of all, scan this QR code. I'll just give you a minute or two. By the way, the slides have been updated. All right. Let me just clarify this once. A by B modulo M equals A modulo M into X modulo M whole modulo M, where X is an inverse mod of B with respect to M. All right. Here, another minute. Please do it fast. Then I will take up doubts and then we wrap up the session. I hope you guys are done by now. Let me just check the chat once. Are there any doubts? Yeah. Thank you, Sean. Yes, clarified that. And let us see Slido. Yeah, QR I had just showed. If anyone else is still left, I will show it. All right. And please rate the session. There is a poll over there. All right. Please rate the session. And yeah, this is the QR code for attendance one last time. Now, similarly, there is a feedback form. Please fill that so that we can help improve our sessions for future. All right. This is not the last session. There'll be many more to come. And for students of IIT Madras, there are new people coming, there are old people going, but the activities will go on. So please do rate us. Please give us our valuable feedback so that we can improve our sessions. All right. And thank you very much. It was a pleasure taking this session. All right. Happy solving, happy coding. I take my leave.